Hi, with this video we start our discussion on numerical methods for ordinary differential equations, or ODEs for short. Okay. We know that many problems in physics and engineering are modeled using differential equations, and in some cases ordinary differential equations. Consider as a very simple example this first order ODE. Okay. Here the unknown is function y of x, and the equation is called differential because it involves derivatives of y with respect to x, and because it's a first derivative, that's why it is first order. And in this equation, f is a given function of x and y. We know that for the solution to this problem to be unique, it must be complemented with an initial condition. And in this case, we consider y of a prescribed to some given value alpha. Okay. We obtain hereby an initial value problem. Under some hypotheses, this initial value problem has a unique solution. And this unique solution can be found analytically in some simple cases. Okay? For instance, case 1, consider an ODE where f depends only on x but not on y. Then, well, this is a simple problem of integration. Y of x is a primitive of f plus a constant c to be determined with the help of the initial condition. Consider now this first order linear ODE where f of xy is simply c times y together with this initial condition. Well, the analytical solution of this ODE, we all know that it's simply alpha times the exponential of cx. Okay? Consider finally this ODE where now the right hand side term f depends both on x and y. Well, in this case the general solution to the ODE is this one where c again has to be determined with the help of the initial condition. Okay. Apart from these simple cases and others, in many situations the analytical solution is unknown, is unavailable, so we will resort in this case to numerical methods. Before going into that, let us illustrate with an example in hydraulics. Okay. That is the determination of backwater curves in channels. Okay. Consider a prismatic channel of width b, constant width b, yx is the water level. Okay. Let q be the flow. y0 is the slope of the baseline. Okay, so y0 is this slope, and the goal is to determine the water level y of x. Okay. Now, first step is physical modeling, in this case hydraulics. Okay. The usual hypothesis here is stationary gradually varied flow. We assume a prismatic channel with small slope below 5%, with no water inflow or outflow. Okay? And we assume that the hydrostatic pressure is, we assume that the pressure distribution is hydrostatic in all normal sections. Now, under these conditions, the water flow can be modeled by means of this first order ODE, which establishes that dy dx is equal to this right-hand side term that contains all our hydraulic modeling. Okay? We will not go into all hydraulic details or of where this comes from. Let me just mention that we have these hydraulic geometric quantities like wetted area or wetted perimeter that have these particularly simple expressions because we are considering a rectangular channel. Now, the hydraulic radius is simply the wetted area over the wetted perimeter. The hydraulic width is B because of our rectangular channel. And then we have Freud's number, that is this dimensionless number that can be understood as the ratio of flow inertia over gravity. First order ODE, we need one initial condition. Well, our hydraulic modeling also tells us that depending on whether we are considering subcritical flow or supercritical flow, the initial condition is required downstream or upstream. So what is important here is that we need to prescribe one of these two initial conditions. We cannot prescribe two initial conditions for a first order ODE. This would lead to a problem with no solution. Okay, after this example, which we will solve later, let us start discussing numerical methods based on finding difference approximation of the derivative. We will work with this initial value problem, first order ODE, dy dx of x equals a given function f of xy in interval ab, together with this initial condition. Okay, so first thing we do is divide interval ab with a partition, okay? And for the moment we'll be assuming that these basis points are equispaced, so this is distance h. We will use throughout this unit the following notation. Lowercase y will denote the analytical solution, so yi is y evaluated at basis point xi, and we will use uppercase y to denote the numerical approximation. So big yi is an approximation to small y in xi. Let us start with the simplest method, with Euler's method. We'll start by saying that if the ODE must hold for any point in AB, in particular, it has to hold for the basis point xi. So dy dx in xi has to be equal to f in xi yi. And then what we do is approximate the derivative in xi. And for that, the key idea is a Taylor expansion. Okay? So what we say is that y in I plus 1 equals y in I plus the step size h times the first derivative in xi plus higher order terms. So first thing we can do here is obtain this approximation to the first derivative. So dy dx in xi equals y in I plus 1 minus yi over h. So this is a forward approximation minus this truncation error. And this truncation error is first order in h proportional to h, simply because tau ih comes from this big O h squared divided over h. Big O h squared divided over h. What we're going to do now is, in this expression, replace f xi yi here to obtain this identity. Please note that in this equation we are working with analytical exact values, okay, because we are taking into account these truncation errors. What we do now to obtain Euler's numerical method is neglect these truncation errors and go from lowercase y to uppercase y. So this boxed equation is one step of Euler's method. Let us illustrate this graphically. Euler's method is this simple stepping strategy where we start by setting y0 to alpha according to the initial condition. Okay? So for point x0 equal to the left edge of the interval a, y0 is the given value of alpha. And then what we do is compute f x0 y0, which can be regarded as the slope of this line tangent to the analytical solution y of x. Okay? Of course, in a realistic application of Euler's method, this line, this analytical solution, is not available. This is precisely what we are trying to approximate, but it's displayed in this figure for illustrative purposes. Okay? Now, according to the stepping strategy of Euler's method, y1 is simply y0 plus h of f x0 y0, and this is how we obtain this y1. Okay? So indeed we go from this point to this point with the constant slope evaluated at x0. Okay? Now, second step of Euler's method. Second step of Euler's method tells us that y2 equals y1 plus h of f x1 y1, which means that we need to compute this second slope to go from x1 y1 to x2 y2, okay? And so on. Okay? So as we can see, with this numerical method, we approximate the line, the curve y of x, by means of this polygonal line. Let us illustrate how this method works for the hydraulic example on backwater water level curves that we discussed previously. We're considering a supercritical flow, and imagine that our reference solution, correct to 10 significant digits, is this one. We are showing here the solution obtained with Euler's method by increasing the number of subintervals, going from 10 to 100, 1,000, and 10,000 intervals. Okay? These values here are the approximated values, and what we are portraying here is the error between the very accurate, exact between quotes solution and the approximation provided by Euler's method. Okay. And we can see here how the error is proportional to h. We can see here how Euler's method is a first-order method. Okay. In Euler's method, if we double the number of steps, the error is reduced by a factor 2. Okay. If we multiply the number of steps by 20, the error is reduced by a factor 20. In other words, Euler's method is convergent. The numerical solution gets more and more accurate as we increase the number m of subintervals, or in other words, as we reduce the number h of, as we reduce the step size h. Okay? We can see here the analytical solution in red, and this is the solution for 4 steps. This is the solution for 8 steps. Okay. Euler's polygonal lines converge to the analytical solution. Okay. Is it possible to obtain numerical methods for ODEs of higher order? Can we think of a method where the approximation error decreases not as h, but maybe as h squared, h cubed, or even h4? The answer is yes, such methods exist. They are the so-called Runge-Kutta method. Okay? These methods, instead of being based on the approximation of the derivative, are based on integration. Consider the following idea. We start with our first order ODE, okay? And what we do is integrate the left-hand side and right-hand side of the equation over a subinterval xi plus 1. Now, of course, in the left-hand side, we obtain simply the difference between yi plus 1 and yi, and in the right-hand side, we retain the integral of function f. Well, the basic idea of Runge-Kutta methods is simply to use a numerical quadrature to approximate this integral in the right-hand side. Okay? So we clearly connect to everything we learned about numerical integration in our previous unit. For instance, we may use the trapezoidal rule to compute this integral, okay? And then we obtain this expression here. Note how we are using xi and xi plus 1 as integration points. And note also that this method is implicit in the following sense. We want to compute yi plus 1, but we need to evaluate in the right-hand side f at yi plus 1. Okay? So Heun's method is an explicit version of the trapezoidal rule that is second-order accurate, which means that the error decreases as h squared. Okay? So what we do in Heun's method is we start with an Euler step. Okay? Note that this step is the same we would use with Euler's method. And what we obtain from here is an approximation, let's call it prediction, to the value at yi plus 1. And then this prediction we use in the right-hand side to obtain the final value yi I plus 1. Note how, in this case, this equation is explicit. If we use the usual notation of k's for the slopes, we have k1 and k2, and Heun's method can be understood as advancing with the average of two slopes, k1 and k2, evaluated at the two edges of the subinterval. Let us illustrate with one step of Heun's method. So in xi, yi, we evaluate slope k1. Okay, so this is k1. So that this point here is our prediction y I plus 1 start. In this point, we evaluate a second slope k2. Okay, so this is slope k2. And finally, the idea of Heun's method is that we march half the step with k1. So this is k1. And half the step with k2. So this line parallel to this one. Heun's method is second order accurate because we now take into account that the slope changes inside the subinterval. We are not assuming a constant slope in the subinterval as we did with Euler's method. Okay. Heun's method is just one member of the family of Runge-Kutta methods. There are other methods, and the basic idea is that with more slopes we can obtain higher order. For instance, it is possible to obtain a fourth order method if we use within each step 1, 2, 3, 4 slopes evaluated like that, and then give them weights 1, 6, 2, 6, 2, 6, and 1, 6 in advancing through the step. Okay? Fourth order, meaning that the error decreases as h to the power of 4, which is very accurate. This means, for instance, that if the step size decreases by a factor of 10, the accuracy increases by a factor of 10 to the power of 4 by a factor of 10,000.